lecture 5 of metallurgy, we will be dealing with the topic Ellingson diagram. So Ellingson diagram is a very important concept which is important from the examination point of view. So you have to concentrate more on what is Ellingson diagram. So before getting into Ellingson diagram, how is it related to our concept of metallurgy, we have to study now. So in the last session, we have discussed about smelting, that is the process of conversion of metal oxide into its metal by the use of a reducing agent, which can be carbon as a reducing agent, carbon monoxide, or it can be a metal like aluminium. So this was the thing which we have studied in the last session about smelting process. So for this particular reaction, how does it proceed? Is it a spontaneous reaction, that is it takes place on its own, or is it a non-spontaneous reaction? It depends upon what is called as your thermodynamic principle. So before getting into the reactivity of this reaction by the use of this reducing agent, we have to study about its thermodynamic principle. So thermodynamic principle is nothing but, here for a reaction to be spontaneous, that is a reaction converting from metal oxide to its metallic form in the presence of a reducing agent, it should be, if we want to know it whether this reaction is a spontaneous reaction or a non-spontaneous reaction, we have to study about its Gibbs free energy, which is your thermodynamic principle. So here we will be studying about what is called as the Gibbs free energy and its relation. So this is the thermodynamic relation which is related Gibbs free energy with delta G is equal to delta H minus T delta S, where delta G is Gibbs free energy, that is change in Gibbs free energy, and delta H represents enthalpy change, and here T stands for temperature and delta S stands for entropy. So if you see a reaction to be spontaneous, so in the previous example, that is a reaction of smelting, that is metal oxide converted into its metallic form. That reaction, in order to know whether that reaction is spontaneous or not, the delta G value must be negative. If delta G value is negative, then we say that a reaction is said to be spontaneous. If delta G value is positive, we say that the reaction is non-spontaneous. Here spontaneous means that a reaction will complete on its own with the energy what we have supplied as in the form of enthalpy. So here Gibbs free energy is nothing but, how can we define Gibbs free energy? The energy required by the system to do useful work for the completion of a reaction is called as Gibbs free energy. So as I have said you, if Gibbs free energy is negative, then we say that the reaction is said to be spontaneous. So we will take one particular example and we will observe the values of Gibbs free energy so that we will understand it much better. So if we take an example here we are seeing this is iron oxide getting converted into its iron and oxygen. So this is a reaction where we are not using any reducing agent, and if you look at the delta G value, it is positive. As I have said you earlier, if the delta G value is positive, it becomes a non-spontaneous reaction, that is the reaction is not feasible. Then what happens if I go for another particular reaction where carbon along with oxygen, when it is combining, it is forming carbon monoxide, where if I look, the delta G value of this particular reaction is found to be negative. It is minus 100 and it's a feasible reaction. So what we are doing here, we are combining these two reactions, that is we are adding carbon in the form of a reducing agent to this particular reaction so that our reaction rate is attained, or the reaction becomes spontaneous. So that's why the reducing agent or carbon is acting as a reducing agent, where it is accepting the oxygen from iron and it is converted into carbon monoxide, and iron is effectively getting reduced to iron oxide is getting reduced to iron. Here if you look for the delta G value, so these two equations if we combine, we are getting this combined equation where the delta G value is found to be minus 60. So if it is negative, we know that it's a spontaneous reaction. So here in this particular reaction, if you observe, the reaction is not feasible if there is no reducing agent. Only when we add a reducing agent, the reaction becomes feasible. So that's why this is the role played by the reducing agent for a reaction to happen spontaneously. We require a reducing agent. So this is the role of a reducing agent for converting our iron oxide into iron by making the reaction spontaneous, in which the delta G value is found to be negative. Okay. Now, Ellingson diagram in particular. Now, this is the thermodynamic principle of your thermodynamic principle, which shows the reaction to be spontaneous. The delta G value must be negative. So here we have to definitely use a reducing agent. So which type of reducing agent should be used for the reduction of metal oxide into its metallic form is given by our what is called as our Ellingson diagram. So Ellingson diagram here gives us what is the suitable reducing agent for a metal oxide to convert into its metal. So this is the speciality of Ellingson diagram. So Ellingson diagram is giving the suitable reducing agent for the conversion of its metal oxide into its particular metal. So we will look into the important points of Ellingson diagram, and what is Ellingson diagram I will display here, then you will understand it. So this is your graphical representation of Ellingson diagram. If you see what are the basic points of Ellingson diagram, I will be discussing now. So Ellingson diagram is a plot between temperature on x-axis and Gibbs free energy of oxygen on y-axis. Here you can see this is the temperature which is given in both degree Celsius as well as in Kelvin, whereas on the y-axis you can see the Gibbs free energy, and that too you are seeing the negative values of Gibbs free energy, that is from 0 to minus 100, minus 200, 300, 400 and so on. So this is a plot between Gibbs free energy and temperature. This is the first important point of Ellingson diagram. And the next point, if you see here, we can see all the lines or the curves on the graph, where these curves are representing, if you see one of the equation here, magnesium is combining with oxygen to give magnesium oxide. So all metals are converted from their metallic form to their oxide forms. So they are converting. So here copper reacting with oxygen, it is forming into its oxide form. Okay, cupric oxide. So like that, here the Ellingson diagram is showing the representation of metal reacting with oxygen to give metallic oxide. But here we need smelting process is the reverse. Reverse is nothing but we are seeing oxide form is getting converted into the metal form. That delta G values is required. But Ellingson diagram shows a plot where all the lines are showing in which metals are reacting with oxygen to form metal oxides. Okay. And the third important point you have to observe here is, you can see some of the graphs, they are not straight. They are not straight lines. They are not increasing straightly. But you can see an abrupt change in the curves. That is, it is moving like this with a straight curve, and then it is changing its direction. And the third important point here you can see is, when if you see the plot of aluminium is going with a straight line, and then it is bending again, and it is going like this. So this bending of the line is showing that there is a phase change. That is, aluminium during its conversion from aluminium, when it is reacting with oxygen, it is forming Al2O3. So the abrupt change in the plot shows that there is a phase change. Phase change here means that the metal may be converted from solid to liquid form or from liquid to gaseous form. So that is what, if there is a straight line, increasing straight line, it means that there is no phase change. But if you see any plot which is not straight, it is showing any abrupt change, which means that there is a change in the phase. That is, a metal may convert from solid to liquid or from liquid to gaseous form. So this is all about these are important points of Ellingson diagram. So the first point, as I'll repeat once again, as I have said you, Ellingson diagram is generally used to give a particular or a specific reducing agent, to choose a specific reducing agent for the conversion of metal oxide into its metal. That is the first point. And if you see the important features of Ellingson diagram, the diagram is a plot between temperature versus Gibbs free energy of oxygen. And here, the lines which are shown here, the plot which is shown here is showing the conversion of metal reacting with oxygen into metal oxide. But the values of delta G we need is conversion of oxide into its metal form. So these values we have to take it in the reverse way. Okay, the diagram is showing the conversion of metal into its metal oxide, but we need in the smelting process metal oxide converting into the metal form. So that is the important point which you have to notice here. And the third point is, if you see any line which is not straight, which is abruptly changing its direction, it means that there is a phase change. Here the best example is aluminium reacting with oxygen Al2O3. You can see that it is bending. The line is bending. The line is bending, which means that here aluminium is converting from solid phase into the liquid phase. So any abrupt change is nothing but there is a change in the phase from solid to liquid or liquid to gas. Now we will see the application part of Ellingson diagram. So Ellingson diagram, as I have said you, it will give the suitable reducing agent. So if we'll take a question here, can carbon reduce ZnO to Zn at 1000 Kelvin and 1500 Kelvin? I'll write both the equations and the Gibbs free energy from the tabular column, then I will tell you. So if you see here, in this, okay. So in this here, carbon on reacting with oxygen, it gives carbon monoxide. The delta G value is found out to be minus 400 kilojoules per mole. This is at 1000 Kelvin. And zinc oxide converting into its corresponding metal, the delta G value is found to be plus 550. As I have, where did I get these delta G values? It is from the graphs. If you look into the graph here, at 1000 Kelvin, nearly at 1000 Kelvin, if you take this plot, that is Zn plus O2 gives rise to Zno, at 1000 Kelvin, the value of delta G is here, it's around minus 550. Whereas for carbon getting converted into its carbon monoxide, its value is nearly around minus 400 at 1000 Kelvin. So this delta G values of these particular equations, I have taken it from this Ellingson diagram. We are getting these delta G values from the Ellingson diagram only. Okay. So the Ellingson diagram gives us the delta G values, and here you can observe zinc oxide converting into zinc metal and its oxygen. I have taken it as plus 550. Here the plot is for zinc getting converted into zinc oxide, but I am taking the reverse equation here. For reverse equation, that's why I have taken the symbol as plus 550 but not negative. Okay. So what is happening when we combine these two equations? We found out that the difference in these delta G values, when we add these delta G values, the delta G value is found to be plus 150. Here, as I have said you, if the delta G value is positive, the reaction is said to be non-spontaneous. If the reaction wanted to be spontaneous, it should be negative. So at this temperature, this reducing agent is not suitable for Zn oxide getting converted into its metal. Then for the other temperature, if you see for 1500 Kelvin, you can look out the delta G values at 1500 Kelvin for zinc as well as carbon. You will see that the delta G value will be found out to be negative, which means that at this temperature, carbon is a very good suitable agent for zinc oxide to get converted into its zinc. Okay. So this is how Ellingson diagram is very useful in predicting the suitable reagent for a particular metal oxide to get reduced into its metal. If you see here, this is the best example I have explained here. At two different temperatures, carbon is a good reducing agent at both the temperatures. We can see that at one temperature, the delta G value is found to be positive. At the other temperature, the delta G value is negative. So as the delta G value of is negative, which means that it acts as a reducing agent at that particular temperature only. So this is all about the Ellingson diagram. So Ellingson diagram gives us a particular reducing agent, and here the most important point which you can remember is any plot, the plots or the lines can be act as a reducing agent if they are below the metal. If they are not exceeding or crossing the metal straight lines. Okay. So this is how Ellingson diagram is useful for predicting the reducing agent. Okay. So this completes Ellingson diagram, which is very useful from the examination point of view.